very kindly they put me as the last talk of the day. I'm here standing between you and your beers. If you don't have any disability, just stand up a minute. Just stand up. Stand up, come on. I'm not going to start unless you stand up. And jump up and down 3 times. Perfect. Okay, great. So, perfect. So, I'm going to talk today about some of the design patterns which I was forced to document when writing a book right here. So I started writing and designing for scalability many years ago, probably let's say 3 years ago. The first, how many of you have written a book here? Okay, Robert as well, yeah. So the first piece of advice I can give you is if you're writing a book and your girlfriend comes up one morning and says, I'm pregnant, you start jumping up and down with joy saying, great, but then you've got 8 months to finish that book before and this book was supposed to be finished, Now, little Peter is 18 months old, he's running around, and we're almost getting there now. So that's the first piece of advice. When I first wrote the first Erlang book, it was fairly easy, and even the first part of this book here as well. I teach a lot, I developed a lot of the training material at Erlang Solutions. So what I did is I took all of those examples, which are short, compact, they have to fit on a PowerPoint slide, and I wrote the book around that. So I just go in, I start writing. So when I start writing, I lecture. All I do is lecture. I've got the tours many kinds, and then once I've written the chapter, I go back and I start thinking, okay, where did students struggle? I go back and I refill all of that, and rewrite, make sure that the parts where they struggle is really clear, so there's no doubt about what I'm writing. And when I'm done, I go back and think, okay, they're really smart students. What questions did they ask? Which I didn't cover in the course, and that's where you start getting your side notes. And then once all of that's done, you go in, look at the documentation, and make sure you've not missed anything. And that was really easy for this book when it came to generic servers, finite state machines, event handlers. The first 10 chapters, I was pumping them out at about a chapter every other month. And that worked really well. Then I got to chapter 11, system principles and release handling. Yes, I think we've heard it from Torben today. Not that easy, and mainly because there's no standardized way of doing things, and also I was just joining together two parts of the training material, and even chapter 12 on software upgrade, that was fairly tough as well, because in both cases what you were trying to do is show how easy it is. You don't want to scare people off, and 40 pages later, it took 40 pages to compress both software upgrade and release handling into maybe 5 easy steps to follow. And I thought, it was done, great, I've got one chapter left, 13. 13 is never a good number. And we'd call that chapter Node Architecture. And that's really where I got stuck. What I was trying to do, talk about is, describe how you're going to architect your Erlang system. How do you expose, all the secret sauce of Erlang scalability and reliability, There used to be a popular belief that by magic you use Erlang, and guess what? Your system's going to scale, and it will never go down. So when doing so, I realized, I've been architecting Erlang systems. I started working with Erlang back in 1994 with Robert at the computer science lab. I did my thesis there, and it took a while before they allowed me to architect systems, but I've architected quite a few, and all of a sudden, I was documenting something for which there was no training material. And so, I started writing chapter 13, doing a brain dump, trying to describe all of the patterns, all of the gotchas, everything you need to think about, everything which you had to reapply between projects. And you're designing a distributed, scalable, fault-tolerant system. And quickly came to realize there was no one-size-fits-all. And I was trying to figure out, when did I start writing this chapter? And I was actually digging through my emails on the plane early this morning, and found an email to my editor saying, oh, I'm almost done. It was dated March 3rd or March 4th. And I'm almost done. I will be sending you what I have. And probably 2 months later, I sent everything off to my editor, who came back and said, help, stop. This is not a chapter, this is 4 chapters. Threw it back to me, and working away, we ended up, working away, we ended up breaking that 1 chapter into 4 separate chapters, which we finally submitted on Sunday. It will soon be available as early release. And it came to the conclusion, that you need to break down the problem. There's no one size fits all, because there are a lot of small different components and design choices you need to make along the way. And what it ended up is, the result of these 4 chapters are, what are the 10 easy steps to designing and architecting a distributed system. So this doesn't just apply to Erlang, it doesn't just apply to Elixir. It will most probably apply to any distributed system you have. And these are the design facts you need to be aware of all along the way. Now, using Erlang or an Erlang-based language makes it much, much easier because of the semantics and because of the Erlang VM and a lot of the properties. But what I can say is going to be abstracted very much. And finally, the conclusion after having written these 4 chapters are that concurrency and distribution is equal to availability and scalability. And when all you're doing when you're designing your system is making choices and trade-offs along the way. And what I'm going to talk through today now are some of these choices you need to make and some of the things you need to think about. Now, the first step you need to do is, when dealing with it, is start looking at your distributed architecture. And distribution here in this case is important, and it's going to become even more important as we start getting more and more cores on our architecture. Amdahl's law will state that your Erlang VM will scale only to a certain number of cores. You want to start utilizing all your cores, that's where distribution starts coming in. And when we look at distribution, OTP has done a great job at putting in place all of the terminology for one single node, if you've ever thought of it. And then for everything else, everyone used different terms and different terminologies to pretty much describe the same thing, causing a massive amount of confusion. And that's when Torben, about 2 years ago, started saying, we need to standardize this. And as part of the release project, he picked everyone's brains, and we put together a document called DECO, which is a distributed Erlang component ontology document. And what we came up with was that if you look at nodes, you need to split up nodes into specific node types. And you usually, in Erlang at least, you've got 3 different types of nodes. You have what we call the front-end nodes, and these are usually client-facing nodes, usually have a lot of TCP/IP-based connections, are often located in, just within your perimeter network, often within a DMZ for security reasons. You then have your logic nodes. The logic nodes are the nodes which run all your business logic. So everything which is, has to do with the application you're writing. And finally, you've got what we call service nodes. And the service nodes will provide some form of service. It could be a database, it could be an API towards a third-party system, it could be an authentication server. So it's, microservices at its best, even before the term was invented. Now, when you're architecting, the first thing you need to do when you're architecting your system is try to break down what you're trying to do into node types, where each node type has a specific responsibility. So, pretend that this was an e-commerce store. Your front end would handle your app APIs or would run web servers. Your business logic would handle all of your transactions, your shopping carts, your session, and then your service nodes could handle payments. It could handle send APIs towards the warehouse to send everything. We could have the databases storing user information, storing anything else. So what you do is when you start dividing all your nodes into the front-end logical nodes and service nodes, you try to reduce the functionality in them, as this allows you then to go in and optimize the hardware, fine-tune the OS, fine-tune the VM. Because the less they do, the more likely they are to become either just I/O bound, or just memory bound, or just CPU bound. And if a system is just CPU bound, it's really easy to optimize. If it's memory bound, it's really easy to optimize. You start putting too much functionality into a single node, you start hitting your head against the wall, because you've got a lot to optimize, and there's also much more which can go wrong, if you think of it. So once you've split up your whole architecture into node type, you need to start thinking about your distributed patterns you want to use. Distributed architectural patterns come in any shapes and sizes, and it very much depends on how you want your fault tolerance of the system to be and how you want it to scale. Now, the most common distributed pattern is distributed Erlang, just the fully, where nodes are all fully connected to each other. And that's really easy. It will just go in and work out of the box. But as we know, it's got its limitations. Every node will connect to all the other nodes, and then it will start sending, if you sniff the network, you'll see the TikTok request, so it will start sending keep alives and health checks towards all the other nodes, and the more nodes you add, the more problematic it gets. And as soon as you start hitting somewhere between 70 to 100 nodes, depending on your configuration, network, and so on, that's when you start seeing a big degradation in throughput. So, distributed Erlang, however, probably 90% of all of the projects, it's good enough. Now, for those where you need a completely different level of scalability, this is where I had to steal the Basho ring. And Turbin was lying, actually. If Turbin, he said, his bonus is based on how many times he shows the ring. No, if a Bash engineer is showing you a presentation and doesn't have the ring, he's actually not being paid. So he's doing it in his own spare time if it doesn't have the ring. Yeah. So the next step is React Core, and React Core basically allows you to you hash your key. Turbin explained it pretty well, but what you do is you've got a key space. It could be your session ID, or it could be a unique value, a unique key, and you basically go in and hash it between 0 and a very large number. And then you partition each key space into 32 or 64 partitions. And you then use these partitions, these partitions being called vNodes, virtual nodes. You then go in and place virtual nodes onto physical nodes. So when you go in and you, assuming you have a session, you go in and you hash on it, you get passed onto the virtual node, which then passes you onto the physical node. So it becomes, in effect, a router, it becomes a job scheduler, and it becomes just a gigantic switch. And now React Core still uses distributed Erlang. That means you're still limited to about 70 to 100 nodes, depending on your pattern. But what you start doing is now you start using your React Core ring with islands of services. So you start putting all of your service nodes and all of your front-end nodes connected to this massive ring right here. And you can then dynamically scale up and scale down your ring as you want. And with a ring, a fully connected ring, I can guarantee you can run WhatsApp size, or even, well, less, you can run Twitter size messaging. And that's enough to reroute all your requests, handle all your tasks and jobs, and then pass them on to the service nodes. And then the real scalability then ends up being on the service nodes themselves. You following me here? Yeah.
Are those service nodes not using distributed Erlang?
I will get to that in a second. No, they don't have to use distributed Erlang.
So you switch on something else?
Yes. So this would be React Core. This is all using distributed Erlang, but here you could use TCP/IP, SSL, AMQP, you name it. And I'm going to get to that in a second, actually. Yeah. And so yeah, you basically get Dynamo style scalability with React Core. And another very common distributed architecture, which you might want to pick, is service orchestration. Very enterprisey by some, but it's being used out there. You have your service bus, and then connected to that service bus, you've got your service nodes, you've got your front-end nodes, and you can also create, again, smaller clusters of nodes where there's just one of the nodes connected to the service bus. And this is a very common architecture as well, where the limits of your scalability is how much your service bus is able to scale. And one of the things you need to think about when you're deciding which distributed pattern to work on is what scalability you want your system to achieve, and what levels of reliability and availability. Because these are all things which, when put together, go head to head with each other. And your whole architecture will basically consist of a set of trade-offs between all of these. And there's no one-size-fits-all, as I mentioned, so you really need distributed frameworks. Most of the time when I get called in to look at such an architecture where they've gone in and they've started using RabbitMQ, or they've started using lots of different nodes, and you go in and you ask, what throughput are you seeing? Oh, we've got 500 requests per second. It's great. You don't need service buses for this. Oh, we can add service. You can do it anyhow. Just simple cluster. Even going up to 20, 30,000 requests per second. A simple mesh cluster is usually more than enough. And another really interesting architecture is, well, obviously the most distributed, scalable distributed system of them all is peer-to-peer, where each client also acts as a server. Think of Kazan, think of BitTorrent. And I've never actually seen an Erlang system scale using a peer-to-peer system, but it would be a really, really interesting one if you need to scale infinitely. And obviously, just like all the other cases, you can have your islands, alongside. So your whole peer-to-peer network here becomes also a giant switch. You almost start applying software-defined networking principles to them, or ATM principles to it. Now, a really interesting question came earlier, and so once you've decided what distributed pattern you want to choose, you need to pick what network protocols you want your nodes to communicate with. And even there's no one-size-fits-all. You might have clusters which use distributed Erlang, but there might be cases where security will allow you to use distributed Erlang. Here's just a typical example of a two-tier architecture where we've got our web servers running in a DMZ. Now, outside the clients are running in the perimeter network, and then we've got firewalls, and then between the firewalls we've got our nodes running the business logic. Last thing you want to do is start running distributed Erlang between the web server and these nodes. You access your web servers. I think the days when we used to work with security by obscurity, when no one knows Erlang, are gone. You get in, oh, cool, distributed Erlang. You then get access to everything. To everything happening here in the business logic. So usually, you need to decide, what network do you want, what network connectivity do you want, what network protocols do you want between the nodes. So in this particular case, for example, maybe SSL or sockets, just pure sockets, where you've got layers here controlling the functions coming in, the requests coming in, and ensuring that only authenticated users can come through. But design your distributed Erlang, MPI, 0MQ, UDP, SSL, sockets, REST, MQP, SNMP, XMPP, MQTT. You can pick anything you want as long as it's not Corba. Another reason to not always use distributed Erlang is bottlenecks. You'll often, well, not often, actually, you'll rarely, but it will happen, come across bottlenecks. We had a system running distributed Erlang all of a sudden, and it was handling instant messages, and it was managing tens of thousands of requests per second. We moved over from instant messaging to email, and distributed Erlang became the bottleneck. And we solved it running, having open TCP/IP connections. Splunk had similar problems. They do a lot of Erlang these days, and they've actually implemented a library. I think it's called GenRPC, which creates pools of sockets in between nodes, and they're able to manage. They were able to scale it up to about 60,000 RPC requests per second in between two nodes. And their biggest problem they're trying to solve is pushing lots of logs from one point to another, from one node to another. So once you've picked your network, the next thing you need to do is go in and define your node interfaces. So you need to define a high-level API which each node, so you've split up all your functionality into smaller nodes. You need to go in and figure out what APIs will these nodes export. So don't worry about the internals, the architecture internals of your node yet. You want to know, if this node calls this node, what API do we want it to call? And how will that communicate? And when doing so, you'll basically validate your choice of the node functionality. Have we put functionality in the right nodes? You want to try to reduce communication between nodes. So when you're designing your API, you're also trying to figure out how you're distributing your data and your state across these nodes. And you want to try to reduce the amount of data redundancy and reduce the communication between the nodes. And once you have your APIs, go back and standardize them. So try to have coherent APIs across all your systems. And these are the first 4 steps. So I think defining node interfaces is not the easiest thing. What I've always found useful is to walk through stories. And when you go through stories, you go, okay, we're going from this node to this node, from this node to that node. And in doing so, you try to figure out what functions jumping from one node to another will call. And that's how you start getting a high-level overview over what you do. And then with the function calls, you start figuring out what data you need to have duplicated on the various nodes in order to handle those calls. Yeah? You're following me here? Yeah, cool. So once you've done that, you need to start thinking about availability. So availability basically defines the uptime of your system over a certain period of time. And us airliners, you often hear us talk about high availability, and that's basically a system which never stops. A system which has to have very, very small downtimes, and that will include software upgrades and maintenance. And the whole point of high availability is the result of your system having no single point of failure. It has to be fault tolerant, it has to be resilient, and it has to be reliable. And all of these have different meanings, which I'm going to go into right now. So let's look at fault tolerance. So fault tolerance refers to the ability of a system to act predictably under failure. And that means that if your system returns an error, if something's gone wrong, your system returns an error, it has acted in a predictable way as long as you've defined that. So, a client sends a request to the front-end server. The front-end server parses it, turns it into an Erlang term, sends it over to the logic node, and somewhere along the way, the logic node crashes. So it could either return an error or a timeout. And the front-end node then sends back an error to the client. This is a fault-tolerant system because it acts predictably. The client knows that a request can either succeed or fail. And so in the client software, we then go in and handle that particular failure. And it could maybe be a retry, or it could be an error shown to the user, or whatnot. And note here how I just refer to this as a simple error. The simple error could be, what could a simple error be?
No reply.
No reply. And so a no reply could be because the request to the logic node never got there. We've got networks in between, and don't believe what they say, that networks are reliable. There's only one thing alongside taxes, deaths, and software bugs which you can be sure of, and that's your network will not be reliable. So it could be that your request got lost. It could be that the response got lost. It could be that the node crashed. It could be that the node had already crashed. It could be that the node is incredibly slow. And it's incredibly slow, and it's queued your request, but it's dealing with so many other things that you get a timeout. It could be that a process in your node has crashed.
Overload.
Overload, yeah, exactly. So it could be a million different things which can happen. The beauty with Erlang is, I don't care. You handle all of these items in exactly the same way. Well, something's gone wrong. And if it's a process which crashed, the supervisor will deal with it. If it's a node crash, Heart will deal with it and restart it. So you're really, you're handling it, you're simplifying everything. Instead of dealing, okay, what happens if there's a network error? What happens if there's a process crash? You just deal with them in exactly the same way. And that will reduce your code size dramatically. On top of fault tolerance, we've got resilience. And resilience is the ability for a system to recover from failure and recover quickly. So a client sends a request, the front-end node terminates, or the back-end terminates, we send back an error. or the client notices it via timeout. We quickly restart this front-end node, and in doing so, we resend the request. The request now makes it to the logic node, and we send back an answer. And assuming the client's aware that you can receive an error, and if it receives an error, it needs to retry, whoever pressed the refresh button or the send button or whatever isn't even aware of the drama happening behind the scenes. So, resilience is the ability of a system to recover from failure. And then on top of that, we've got reliability. And reliability means the ability of a system to function under particular predefined conditions. And this includes errors and inconsistent states. We had a customer who was saying, oh, our system has been up 100%, it's been up. We've had 100% uptime since we went live. When did you go live? Oh, 10, 15 years ago. Oh, wow, that's impressive. And then you start scratching behind the scenes and you realize that their front ends had never gone down. As soon as their logic nodes failed, all they did was log the request, and then someone in back office went in and picked the request and dealt with it manually. So yes, the system had 100% availability, but the reliability was CAC, it was 0. And so it's the two don't go hand in hand. And what you also need to keep in mind when you're dealing with reliability is the whole no single point of failure, where you need at least 2 of everything. Because if something goes wrong, something else goes in and deals with it. And by something going wrong, it's not just software, it's not just hardware, it could be network, it could be a power supply, it could be your system administrator tripping over your network cable. So tons of things which can go wrong. And in this example, when it comes to reliability, the client sends a request, the request gets forwarded to a backend node, so the logic node terminates, or something goes wrong. So the front end, the server itself realizes something's gone wrong, so without telling the client, forwards it to another node. And having done so, a reply is sent back to the client. And once again, the client has no idea something's going wrong behind the scenes. We've managed to isolate the failure and hide it from the client. And and basically this having 2 of everything ensures that if something goes wrong, you have an alternative, you've got a backup. And now, so these are the retry strategies. And there are a total of 3 different retry strategies. So you can, in this case, we've sent a request, we forward the request to the logic node, but we're not sure if this request has succeeded or not. We get some form of error or timeout here, so we go in and retry it here. And this is what we call an at least once attempt. So we've gone in and we've tried something at least once. If it fails, we continue trying it again. So picture an SMS. You're sending an SMS, you hit SMSC, you don't get a response, you hit another SMSC. That means the final result is that you, as a recipient, might receive 2 copies of the same SMS. Has it ever happened? Yeah. This is probably what you've seen here. And it doesn't really matter if that's the case. Now, what happens if you're sending a few billion euros from Brussels to Greece? Twice.
Greece is happy.
Greece is happy. The bureaucrats in Brussels aren't. So that's a typical case when you're dealing with money or stocks or even premium rate SMSs. Is the exactly once principle, where you send a request exactly once. Now, exactly once is not that easy because once you've sent it, and you cannot guarantee it across distributed systems. As soon as you put a network in between, no matter how much you promise your network is unreliable, something can and will go wrong. So what happens is with exactly once is you send a request, and if that request fails, you don't retry. You send back an error. And when sending back an error, you then usually trigger some script which start tracing the call. So, we're moving money from Brussels to Greece. Okay, went from Brussels to Italy. Right? Yeah. Did it reach the bank account in Italy? Yes, it did. I'm Italian, so I'm allowed to. Yes. Oh, great. And well, from Italy, got forwarded on to Greece. Did it ever reach Greece? No. Okay. And you start narrowing it down, and you try to basically clean up after yourselves. And that's what happens in banking. There was a banking system we used to work on where as soon as the exactly once request failed, we had a system called Hagrid, which came along. You know, Hagrid used to always save the kids from trouble at Hogwarts. And in this case, it basically saved us from trouble whenever some of our software went wrong with the network in between. And then finally, you've got a third one, which is at the most once. At the most once is when you fire off your request, but you never ask for an acknowledgement back. Okay? And that means you've sent it off, you could lose it, but you don't really care. And that's also commonly used for SMS. So those times where you never received SMS, that's the strategy they picked for some of the software in between the system, where you send it off, you don't save state, you don't worry, you just get on with your life. And that's the cheapest of them all, because you don't need to wait here for a response. So those are the three things. On top of that, so those are the three retry strategies. On top of that, you need to start thinking, how do you share your data? And how do you share your data across one or more machines? If you need full tolerance, you need at least 2 copies of your data. You need scalability, you need at least 2 copies of your data. So for all your data and state, what you need to do is pick your sharing strategy across nodes, across clusters, and you need to take into consideration as well the needs of your retry strategy. So here's an example. We go in, we send a login request, and we start, client 1 is logged in and his session is stored here. This is a share nothing approach. Client 2 goes in, logs in, and session 2 is stored here. We lose a backend node, so we lose a logic node and a service node. We go in and we restart. Client 1 tries to log in, and he's forwarded now to this database, which only has session 2 and not session 1. So we send back an error unknown session. So the client, being told that your session's not valid, goes in and logs on again. And he will log on, and now this node, which is still up, will have both sessions. And this is the share nothing architecture, which is obviously also the most scalable. It's equivalent to sharding. We've got the share something, where we might go in and share session, but not share specific data within that session. So assume you've got an e-commerce site. You've got a user who logs on, so he starts a session, and we store the session on 2 separate machines. Then he goes in and starts buying a book, but the shopping cart is not saved across 2 machines. So we only store the book in one of the machines. We lose that node, and he goes in and buys a train set. That train set now gets stored on another machine right here. And that's the share something. You share some of your state, but not everything. A lot of things can happen. There's no good restart. You could then merge the 2 shopping baskets together. That's what Amazon does. It could be a network partition. There are lots of things you need to think about. Lots of strategy. And finally, you've got to share everything. This is an example we call primary replication. We go in, we buy a book. We store it on both nodes. We go in and we buy a train set, and then we remove a book. And when we remove a book, when this node comes back up again, it will copy all of the data and we'll have consistency. And also, when we're dealing with share everything, we need to think there might be cases where we use eventual consistency, CRDTs, casual consistency, so lots of strategies depending on your business logic. And when taking these choices, you've done a lot of trade-offs here. This is a system which is not available, and as you go along the axis, the more available it becomes. And consistency, you've got casual consistency, weak consistency, and as you go up, you start moving up towards strong consistency, where you're guaranteed the response. And the exactly once approach is strong consistency. But that's also the least available, because if you lose a node, you might have to take your system offline to guarantee consistency. And you've got the least once, at least in the middle, and at most once is obviously the most available, because you just fire and forget. But it's also the least consistent, because you might lose requests along the way, and so your data doesn't become that consistent. And the same applies to reliability. Your share everything is obviously the most reliable. You lose a copy of your data, you've got another copy stored somewhere. But the network traffic becomes really expensive. As soon as you get a network partition, you lose your availability. Once again, you might have to take a system offline. Share something is somewhere in between, and then share nothing, obviously. It's the least reliable, because if you lose a machine, you lose all the data on it. But obviously, it's the most available one. So these are the 5th, 5th, and 6th step. Every interface function, you need to pick a retry strategy, and for all your data and state, pick your sharing strategy across node families. A node family is a group of nodes of the same type. And a group of node families together will give you a cluster, and then your cluster together will give you your whole system. So once you've done these design choices, you might not have realized it, but you've also already made trade-offs which come and are directly associated with your scalability. And when you're scaling out, you have to be very careful and integrated with orchestration and also with your consistency models in your system. And when you're scaling out, most of the time your scaling out means capacity planning. So it's going in and actually proving that your system can handle the load it was designed to handle. And that with time, you can also scale to increase demand without failing or falling down the system. Now, back in the good old days, we used to scale vertically. The feeling of opening that box and having the fastest, shiniest computers. But scaling vertically by buying more powerful hardware is pretty expensive. It is not environmentally friendly, because the bigger the computer gets, the more poisonous the stuff in it. And it's not the way we do things today. Today we scale using commodity servers, commodity hardware. We scale horizontally. And just by throwing more servers at the problem, and then you're sharing data across them. And so, as I mentioned earlier, when you've reached this point, you already have made all your trade-offs in the previous section. And when you look at the consistency, that the most once, as we mentioned, is also the least scalable of your solutions, and only once is the most scalable. And with availability, share everything. Once again, it's the least scalable. Share nothing is the most scalable. And so this is the point where in your capacity planning, you start stress testing your system. You start stress testing your system for 2 reasons. One is to make sure it's stable, to make sure it can handle the load, to optimize bottlenecks and get rid of bottlenecks. And during your capacity planning, you'll most probably go back and revisit many of the architectural assumptions you took in the first round. And luckily, if you've broken everything up into small node types, adding a few more node types, or changing your sharding or the way you partition or share your data won't be that difficult as long as you encapsulated your database in the right way. And so you'll have a few iterations and show that you can handle the load, but also very important is know when to apply back pressure and load regulation. So your back pressure is when you start rejecting calls because your system's overloaded. And load regulation is usually using queuing to scale out your peaks and troughs. So you've got a third-party API, and your third-party API can only handle 100 requests per second. You get 200 requests coming in, you'll queue 100, and you'll take them on a first-come, first-served basis. Yeah. And you've got jobs and safety valve here. Jobs if it's a Viger, by Ulfiger, and safety valve by Jesper Lewis Henderson. And they're two great, they cater for different types of solutions. I think jobs is fairly complicated, but will actually do you coffee in the morning as well. Safety valve is much simpler, much easier, and much easier to get going with, and both work great. And so once you put your back pressure in your load regulation, you need to start thinking about monitoring and preemptive support. But we'll take this another day, as I realize there are probably beers outside waiting for us. But just to review, these are the 10 steps. Split your system's functionality into manageable standalone nodes. You will be optimizing nodes. You will be configuring your whole stack, OS level, VM level, and your code as well, fine-tuning it. Network level as well, for that matter. Decide what distributed architectural pattern you're going to use, and it's often a mixture of architectural patterns, and decide what network protocols you want to use to have your nodes communicate. And once again, there's no one-size-fits-all. It can be a mixture of them. Define your node interfaces, state and data model, and for every interface function, you need to pick a retry strategy. So you need to know if calling this function fails, what retry strategy do I need to do? And this is something I very rarely see done. And this is exactly what leaves your system in an inconsistent state at some point or another. And then finally, for all your data state, pick your sharing strategies across nodes, node families, clusters and systems. And reiterate through all of the steps until you have all the trade-offs which suits what you're trying to do. Look at your cluster grouping, look at how your system's going to scale up and down through time, and identify where to apply back pressure. And last but not least, come back next year and I'll talk about your whole OEM approach. And focus on OEM approach has to be preemptive support. You want 5 nines uptime, that's a few minutes per year. You need to automate a lot of your support. You notice something's going wrong, you need to trigger scripts which deal with it. And also the ability to do post-mortem debugging, you need to have full visibility. And I'll leave you with one last word of advice, and it's do not over-engineer systems. Everyone wants to build the next WhatsApp, the next Facebook, or whatnot. But before you start reaching that scale, you need users, and you need to go live. So start taking a step at a time. If you split up your node into small standalone units, start simple, and then add complexity when you see it. So think lean, solve problems when and where it's an issue. Okay. Any questions? I think we're running way.
Yeah, we were way behind anyway, so
yeah.
that's not your fault. I'm going to say
For those of you who don't know me, Robert and I we're usually the last ones to always get on a plane. Yes.
Well, I don't want to sit there and wait for you.
Yeah, exactly.
Yeah. Anyway, I could just say one comment.
Yeah.
One is, you talk about over-engineering. If you think about it, WhatsApp is actually quite a simple application. Yeah. One of the reasons it worked was because they decided not to over-engineer it and to keep it simple. And also, self-evident. Of course you should do like that. What's the problem? Yes.
I mean, you want to get something up and running, and you don't want to make sure that what you have is going to work. So all of this is the result of trying to formalize what's been going through my head in the last 15 years whenever I've designed a lot of these systems. And I think we just pushed the chapters to arrive. They'll be available as early release. So you'll probably find them on BitTorrent in a week or two. And I've got no problems with it at all. Try before you buy. And if you like it, no one should pay a full price for an O'Reilly book. So use the discount code. We don't set the prices, and they've got but it's no point. They're a fantastic publisher. I can recommend. They've got an amazing team who really support you from beginning to end. But use discount code ALFD for 50% off the early release, the printed copy, and 40% of printed copies. And what I should not be telling you is that this discount code works on all the other O'Reilly books as well. Okay. Okay, thank you very much.